But I'm going to record this. You can always go back and look at it. But I'm going to start presenting. And we'll start with this. I should have taken attendance. All right, morning, everybody. Morning. All right, let's take a look, because I want to give you some time today to work on some stuff, to practice some things before we get to 2.2. But I put this up here for today because I had some stuff that I wanted to make sure you knew, as well as cohort B at home. But can you believe this is the 5th week of school? 5th week of school already. Isn't that crazy? The 17th. Right? Or more than halfway there. Isn't that crazy? So because this week is weird with Wednesdays, all remote day except for seniors. Seniors are taking their SAT on Wednesday. I don't see you again in person until next Monday, which is just not going to fly for me. So you can expect tomorrow and Thursday and maybe Friday having to log on live from home, okay, so that I can get us into 2.2, because here we are halfway through the first quarter, maybe more, and we are not halfway through college algebra yet. So I want to make sure that we had a strong base, and we're going to take today to do that, but then we're going to pick up the pace a little bit and get a little bit further into chapter 2. So it's not ideal. It's not the way that I would love to teach class. Of course, I just want to see you 5 days a week, or block days and then Friday, whatever. It'd be great to see you a lot more, but I just can't wait. I can't. We just got to keep going. So you can always watch the videos, recordings instead or in addition to coming live, but it's just not the best because the quality isn't great. I did get hopefully a much better web camera that will create a slightly better video quality, and I'm going to test that out between today and tomorrow. So fingers crossed that helps, and this is better than the one on the MacBook. Okay. The other thing that's new, attendance in an Infinite Campus on your remote days now has to be done before 10 a.m. Then it locks. Okay, so wake up in the morning, get yourself checked in, and then decide how you want your day to go. Okay. Now, you know me, I was up late last night, and I was checking homework because I wanted to see how you did. And what I noticed that a lot of 2.1b went pretty well, but some of it didn't. Some of us got confused on like number 4 and number 5, more than 1, 2, and 3. And we just either didn't know how to proceed, or we got stuck, or we rounded when we really shouldn't be rounding, stuff like that. So I want to go over 2.1b, that homework, fill in some blanks, give you some advice, give you some good ideas, talk about Friday's sum and difference of perfect cubes lesson, and then give you a chance to try it while you're here. Okay, so let's do that. Take out homework 2.1b, and let's go through some answers one by one. Okay, so take those out. I want you to check to see how you did. I just want to make sure that I'm still recording, that people are at home. Nice. Hi, everybody. You guys are awesome. Thank you for being here at home. I've got you in my ear if you ever need me, so just unmute yourself and ask questions. I'm going to be around a room a little bit today. So take out that homework, check to see how you did. this is your time to like put check marks next to things or put X's and say, practice factoring, or to write the correct answer down if you didn't get it right. Because, I mean, you saw with test number 1, you were able to use those notes, and you know, I trust this class to do the right thing when it comes to stuff like that. So having good, strong notes is going to help you just do well. So take a look, see how you did. I'm going to talk over some things as we go. Okay. For number 1, I wrote a few things down that I didn't really write down the rest of the way. I wrote the negative b over 2a for the vertex, and for vertex form, I wrote kind of the general form. From there on out, I just kind of did the work, and that's not a bad way to do things. Early on, when you have this repeated, 5 questions that are asking you to do the same 6 things, you don't have to write down the formula 6 different times. Write it once, and that's enough for me. I'm okay with that. But this was the easy one because A was 1. It factored nicely. The vertex was rational. Life was good. Questions? All good? Okay. Number 2. Okay, so I took this one up 1 notch by changing A to be something different than 1. But I still made it nice and factorable. The vertex, of course, didn't fall somewhere pretty, but it did fall somewhere perfect. Okay, so negative 16 over 6, so negative 8/3. And then I plug that in, and obviously I'm letting the calculator do that for me, and I want you to do the same. I don't need you to work out that arithmetic. Axis symmetry, orientation, vertex form, all good. And then finding the x-intercepts. If it's factorable, that is definitely going to be your easiest way to go about it. Now, there's lots of different ways to solve quadratic equations, and we'll kind of talk about those once we get a little further, like number 4, number 5 kind of threw us a little bit for a loop along the way. But I see some people writing things down, and that's awesome. That's what I want. And if you're getting stuff right, put a check mark next to it so you feel good about it. Take out a red pen and, be a teacher for a second. Okay. Now, the order that I wrote the solutions for F, I just went from the left side of the number line to the right, which is a good way to do that. So I went -5 and then -1/3, but switch those, that's cool. Even if you switch these, right? If you switched, I'll use this so people at home can see it. If you switch this order right here, if you put the x plus 5 first and then the 3x plus 1, it's not wrong. But that one is a little bit more imperfect. Not incorrect. You're not going to lose points, but imperfect. When we have it written in standard form, we want largest exponent first and then on down. We have it written in factored form. You want the factor with the largest leading coefficient first. So between 3x and x, of course, the 3 is the larger of the 2, so that factor came first rather than the x plus 5. Okay. Again, not incorrect to put x plus 5 times 3x plus 1, but just not ideal. I want to know kind of what those bigger coefficients are, so I'll put them first. Okay, and then I'll get you caught up. Okay, number 3. I wanted to throw some negatives your way to see how comfortable you are dealing with that. So that's the switch here for number 3 is you've got 2 numbers that add to a negative but multiply to a positive. Vertex was nice though, and so for number 2 you couldn't use decimals for that vertex because it was non-terminating, right? It was repeating. It was that negative 2.66666 forever. So you had to use the fraction version, but with this vertex, you could have said 2 1/4 or 2.25 and negative 0.125. That's cool too. You have that freedom to do that, but I urge you to use fractions whenever you can, and you'll see why once we get to stuff like number 5. Okay, and we'll practice with my idea for number 5 and why I like doing something one way more than the other. That was super vague. Sorry about that. But then it factored nicely, right? 2 numbers added to a negative multiplied to a positive, so they're both negative. And in order for these 2 parentheses, the x minus 2 and the x minus 2 to be the same, I had to factor out the -5 to do that. And you get your solutions 2, 2. 2.5 or 5 halves. Okay, and you've got graphing calculators. You know what the answers are, but have the algebra prove that, right? You can look up, you can graph them, see where it runs on the x-axis, find the vertex. You can do all that stuff. I just need the algebra to go with it. If you know what the answers are ahead of time, make sure that the math that you do follows, which is nice. I like to use that. Okay, 1, 2, and 3. Questions? Okay. 4 and 5 is where I saw the mistakes start to creep in, and that's why I wanted to spend some time talking about this. And some of the comments on chapter 1, when I asked you to reflect on chapter 1, some people said spend a little bit more time talking about the homework and making sure that I answer more questions. So if you have questions, please ask them. I'm debating whether I should just show it to you or not. I think I'm just going to do it. I'm going to show you number 4, and then we'll talk about number 5. Okay. Fix your mistakes. Ask questions. But I'm going to talk through it as I can, okay? There is no bx term, which means b is 0. And if b is 0, then negative b over 2a is 0. Which means your vertex has an x value of 0. Which means it is your y-intercept. So your y-intercept and your vertex are going to be the same when you have no bx term, because there's no horizontal shift that's happening in there, which makes your axis symmetry the y-axis, which is x equals 0. And for the first time, we're pointing down. So there's my upside down parabola. You can say negative, you can say open downward, lots of different ways to write down the orientation. But vertex form, you're looking at it. Now, I saw some people put like x plus 0 squared. You don't have to. There's no need, right? X plus 0 is just x. So t of x in standard form is actually already written in vertex form. If you put x plus 0, it's all good. Of course, I wouldn't take off points for you telling me more information. But you don't have to. Writing x plus 0 is not crucial. So I know if you write it like that, that it's in vertex form. So we're good there. But then we got to f. And people either just weren't sure what to do, or they started to round. And both of those are definitely an issue. And like if you wanted to factor, you can factor, but the first kind of factoring that we always look for is a greatest common factor. No matter what, whenever we're doing our factoring, the greatest common factor is the first thing you should always factor out. But then you get into there and you see, okay, I've got difference. I've got two things, and one of them is a perfect square, but the other one isn't. Right? If that was x squared minus 4, okay, x plus 2x minus 2, and great, I'm done. The reality is it can factor. It's just going to be irrational. Right? You want two numbers that add to 0 and multiply to 3? It's the square root of 3 and the square root of 3. One's a plus, one's a minus. And that's a little hard to see factoring because you don't recognize imperfect squares like 3 really being just the perfect square of two irrational numbers. Right? So I like f this way. Right? If you only have one x in the whole problem, just go get it. Go solve for it. Subtract 15, divide by negative 5, take the square root. Whenever you take the square root, we've got the plus or minus in front, which we would get there too, right? Set those two factors equal to 0, negative radical 3 and positive radical 3. But 1.732, the decimal approximation of that is wrong. You cannot say equals if it's not equals. There's only one time I want you to round. That's when I tell you to round. Okay, if I don't say approximate, if I don't say estimate, if I don't say round, don't do it. Always, always, always find the right answer. Okay, and radical 3, square root of 3 is perfect. Okay, so be careful. I saw some people putting the 1.732, or just they didn't know what to do because it wasn't factorable, and I get that. It's not, but it only has one x degree 2. It's okay. But there's only one of them, so we can go get it. Okay, so if you only see one x in the problem, go solve for it. Okay, if you don't, then we'll try to factor, and that's what happened in number 5, right? We got to here, and we could do all the things that we wanted to do. I want to hide some of my solutions. So I'm going to stop it right there, blow it up. Y-intercept and vertex and axis symmetry, vertex form, all that stuff is all good. I can find all that stuff, but we tried to find the x-intercepts, and we ran into the case where two numbers added up to 6 and multiplied to -4, and that's impossible with rational numbers, right? And if it's factorable, we know we have rational x-intercepts. And so some people gave up. Some people got stuck. Some people reached out and asked for help, which was awesome. Because of course I was up till like 1:30 in the morning, my hand deep in a bag of popcorn, trying to stay awake, getting stuff done. And I was checking and I was like, well, there's a lot of good that was happening, which is great. And I know quadratics are old news and it's not super exciting to study all the same stuff, I know, but we need to have quadratics, otherwise we can't do anything else. So this is our last day of quadratics, I promise. Well, exclusively quadratics. So what do? We get to the x-intercepts, 4x squared plus 6x minus 1, and we try our little plus and minus, add to this, multiplies to that, and it doesn't work. How? And I'm going to bring the folks at home with me. So they can see this. How are we going to solve that? Is there anybody that was able to put a dent into that problem? How'd you do it? Perfect. I think that's a great way to start. You've got x, 4x squared plus 6x minus 1 equals 0. I think quadratic formula is probably a way that most of us, if we did get ourselves to the right answer, was a great way to do that. You guys know that one, right? Quadratic formula. X equals -b plus or minus square root of b squared minus 4ac all over 2a. Did your algebra teacher make you sing that song? I hope so. It's the best song ever. Ever seen the video of like this 4-year-old singing that song? Oh, it's so good. YouTube, if we have time, Emily sings. Her name's Emily, not you. But I'm gonna make you two sing. No, I'm just kidding. Emily sings the quadratic formula. And I think her mom's like a math teacher. And she's like singing like Twinkle, Twinkle, Little Star. And her mom's like, sing the x equals song. And she cranks it out. Okay. So we just do it, right? No, -b plus or minus the square root of b squared, I'll go slow, 4ac all over 2 times a. And if you know the quadratic formula, plugging your numbers in isn't all that bad, but all of the work from here lends itself to potential mistakes. And so while it is great and it will work whether you have rational, irrational, or even imaginary roots, 36 plus 16, so 52. You did all your substitution. Now you've multiplied everything together and added and subtracted. But there's more that we can do, and we have to. We need the simplest version of that fraction. And so what can we do first to make things simpler? Right, we have to simplify our radicals. Always. I'm not going to ask you to simplify them. You know you need to do that. We have to simplify radicals. And so I can get myself, I'll come this way, just so I can use a little bit more space. -6 plus or minus 2 root 13 all over 8. And can you do more? Yeah, you've got a common factor of 2 up top. You can simplify that. Now, here's a piece of advice that I'm going to give you because I think it's going to help us when we get to option number 2. I'll show you that one, but also when we get to imaginary roots. You should break apart the rational part of this answer and the irrational part of this answer. Okay, we've got 2 things up top being added and subtracted, all over a single denominator. Okay, when we add fractions, 1/5 plus 2/5, what do you get? 3/5. But the step in between that we don't bother writing is 1 plus 2 over 5. And so I want you to go this way. I want you to start here and end up there. What I want you to do is take the 6, -6 over 8, the plus or minus 2 root 13 over 8, start writing them separately. Because if you remember complex numbers from last year with square roots of negatives, you have to write the real part and the imaginary part separately. So we need to get into the habit of writing the rational and the irrational part separately. Because sometimes, I mean, in this case, they both simplify, right? Divide both of them by 2. But sometimes maybe you don't have a common factor up top in one spot. Like maybe this was -7 plus or minus 2, and you can't simplify the first fraction, but you can simplify the second one. So get in the habit of doing that. And if you haven't done that, if you didn't do that in your homework, it might be a good thing to jot down. Okay, and I'm just going this way, right? If I have 2 things being added or subtracted up top over a single fraction, really 2 or more, I can break them up into that many fractions all over the same denominator. And that's really nice. I like the quadratic formula. We know it works no matter what. Rational, irrational, 1 x-intercept, 2 x-intercepts, 0 x-intercepts. I know that this is going to work and get me there. Okay, but there is another option that I wanted to show you. And when I asked period 2 earlier today which one they preferred after I showed it to them, they actually liked this one better. Okay. Okay. Now I want to see if we can get there. What's the problem with what's boxed in the top there, the 4x squared plus 6x minus 1 equals 0? Why don't we like it? Good, not factorable, okay? And the reason that we even care that it's not factorable is because we've got 2 different terms with x's in them. That's the problem. This isn't like number 4, where it wasn't factorable, but there's only 1 x, so we just went and got it. This one has 2 different powers of x, 2 different degree x terms, right? Degree 2 and a degree 1. Of course, a degree 0, but that one doesn't matter. And it doesn't factor. So we had to rely on the quadratic formula. Well, what if we had a whole other equation that meant the exact same thing, that was the exact same equation, just, let me give myself a little more space, but just written differently, but only had 1 x in it? Vertex form. There is an option to, instead of using the quadratic formula, to solve this equation using vertex form. What was it? 4x, what was it? 3/4 squared minus 13/4. That equation only has 1 x in it, which means we can go solve for it directly just by solving equations, manipulating algebraically as the way we always would. I know the fractions in there are going to throw us off a little bit, but they're just numbers. But I highly recommend fractions here over decimals, and you're going to see why. All right, so let's solve for it. We got to break this out. But we've got lots of other things that we need to move around first before we get into those parentheses. What should we do first? Add 13/4 to both sides. So that's going to slide over there. So 4x plus 3/4 squared equals 13/4 because I added it to both sides. Okay, addition, subtraction done. Next, divide by 4. Now, if I divide the left side by 4, it just cancels out. So I still have this x over x plus 3/4 squared. And if I'm dividing a fraction by 4, I'm going to make the denominator 4 times bigger. Because I'm dividing by 4, which means I'm multiplying by 1/4. So the top stays the same, the denominator gets 4 times bigger. So this becomes 13 over 16. All right, because I can't make the numerator 4 times smaller, it's 13. 4 doesn't go evenly into that. So I have to make the denominator 4 times bigger. Okay, now what? Square root. Good. Square root of the left, square root of the right. When I take the square root of the left, the square and the square root cancel each other out, and now I'm inside the parentheses, so I don't need them anymore. But when I take the square root of a fraction, that is the same as taking the fraction of each individual square root. And so, because we took the square root, of course, we have that plus or minus. Don't forget that. What about the square root of 13? Is that as simple as I can get? Is that the best way to write that number? Yeah, right, because there's no perfect square factors that go into it like we did for 52. So square root of 13 is all we can do. But what about the square root of 16? And if you had written that 13 over 4 as 3 1/4, 3.25, and you took the square root of that, you'd be stuck with the square root of 3.25. Now you've got this rationalized fraction. Already good. I don't have to do any rationalizing in the denominator. Life is good. All I have to do is take this 3/4 and slide it over. Subtraction. Let's put the nice stuff up front. When I say nice, I mean rational. Let's put the irrational stuff at the end. Ta-da. No simplifying of radicals necessary. No rationalizing of denominators. No needing to split stuff apart. You get to the exact same spot, I think, in an easier way. I didn't have to know the quadratic formula. Like, what if I messed up my negatives? What if I forgot how to simplify radicals? What if I didn't break those two apart? So many places to make a mistake, to screw up. Solving with vertex form rather than trying to use a quadratic formula is awesome. I love, love, love it. I think it's so nice to be able to use that. What do you think? You like it? Isn't that cool? I love that. So that's how I did it. When and I'm gonna reshare this screen. When I put my solutions together for this problem, I did it both ways so that you could see it. Come on, share it. This one. I did it both ways. And I just wanted you to, instead of just putting up these answers and saying, hey, look at this, I wanted to walk through that process with you. But look how much shorter, look how much less space it takes up for me to do option 2 than it did to be option 1. Now, I know I took 2 lines to write my big fractions, but that's because I have big fractions. Right? There's a lot of stuff going on in the quadratic formula. That, as nice as it is, you've got another option. And here's the great part. You already did vertex form in the step right before that. So I think that's pretty cool. All right. Do you like that way? I love it. Okay. Let's talk one last thing before getting back to Friday's stuff. But questions 1 through 5, now that we talked about it? You feel pretty good about it? Okay, good. I want to leave this up here for a quick second. I'm going to steal them back. I just wanted to show that to you. Do you know the Muffin Man? I love that scene in Shrek. I just think that's so funny. I'm like, the Muffin Man. Yeah. Do you know how to tell just by looking at a function, a quadratic function, whether or not the roots, x-intercepts, are going to be rational, irrational, or imaginary? Do you know how to determine what I'm going to call the nature of the roots? If it's written x squared plus bx plus c, how can you tell? And so I'm going to leave a little space here because we're going to decide how to do it. How to tell if it's rational, irrational, or imaginary, without really doing a whole bunch of work, without having to try to factor a quadratic formula or find the vertex. Just like a quick look at a function and say, this is the kind of answers I should expect to get. Like, what makes some quadratic give me nice rational roots, not so nice irrational ones, or just the imaginaries? Yeah. What's underneath the square root? Look at what's underneath that square root, right? That's going to make the difference. If that number, what's underneath the square root, is 1, 4, 9, 16, 100, 400, some perfect square, then when I take the square root of that, the square root goes away and it's just some really nice number, right? And so we gave that thing a name. It's called, sorry, the discriminant. The b squared minus 4ac. It's called the discriminant. And it helps us figure out the nature of the roots. So I don't know if you can see that in green there, but that says discriminant, D-I-S-C-R-I-M-I-N-A-N-T, discriminant. And it's not the square root of, it's just what's underneath that square root. Okay? And so if I want rational, like perfect, nice rational roots, what I need is I need that discriminant, the b squared minus 4ac. I need to be a perfect square. Now, it could create one x-intercept or two. And either way, they're going to be rational. But what is that one perfect square that if I put it here, I get a really nice square root? So nice, in fact, that when I add and subtract that same number, it doesn't make a difference. If I put a number under here, and I take the square root, and it's perfect, but the result of that square root gives me a number right here that when I add and subtract it, it makes no difference. 0. If your discriminant is 0, let me write that. Let's say if b squared minus 4ac is exactly 0, your root is the vertex. It's just going to come down, hit the x-axis, or come up, hit the x-axis, and bounce right off. If you get a nice perfect square root, but it's just positive, 1, 4, 9, 16, something like that. If it's a perfect square and it's positive, then we're going to get two nice x-intercepts. And that's the case from the beginning. Like option number 1, it's factorable. This, if your function is factorable, you get rational. And you can do just a quick check to see if it's factorable by just doing b squared minus 4ac and getting a perfect square back. Okay? If you get some irrational roots, if you're expecting irrational roots, it's because the discriminant is not a perfect square. And there are a heck of a lot more imperfect squares than there are perfect squares. The density of the irrational numbers on the number line is a lot higher than the rationals. The density of the irrational. So there are an infinite number of rational numbers, but they're countable. I can count them. The irrational numbers are uncountable. They are uncountably infinite. And maybe we'll get to a point where we can have that conversation about countable infinity. We'll see. Okay. What do I want b squared minus 4ac to result in if my expectation is something imaginary? If I'm going to get roots that don't actually exist, and I don't see, right? I'm looking at a picture that looks like this, or like that. Negative, perfect. Right, and that's what makes those imaginary numbers, right? You have square roots of negatives. And that'll be 2.4. We'll get to complex numbers and kind of just recapping, hopefully, some stuff that you saw maybe last year. There you go. So I just wanted to talk about the discriminant. Have you seen that before? You seem like you knew what you were talking about. B squared minus 4ac, like being a kind of runs the show and the kind of roots that we're going to get. Okay, cool. So there's my just quick little recap that I wanted to make sure we talked about. I thought the discriminant would be a good thing to touch on because it's just nice to know ahead of time what to expect and what not to. But I also want to talk about Friday. And then I just want to give you a chance to try it out. Oh my goodness, we are so short on time. Oh, it's all right. We'll make it work. Okay. Sum and difference of cubes. There's a way that we can factor the sum and difference of perfect cubes. And this is what you saw with me on Friday. And I just wanted to recap it. Okay. if you have some a cubed plus some other number b cubed. Now, it could be plus or it could be minus. I'm going to put a little plus or minus in there. These are factorable. Now, don't forget, the first thing you always want to look for is the greatest common factor. You have to pull out a GCF first before this stuff is going to work. Okay, but if you've done that or it doesn't exist and you're good to go, then we can jump into a factored version of this, where it is a binomial times a trinomial. Okay, the terms are a, b, a squared, ab, b squared. So that's why I wrote it like this, right? Give myself a base cubed. Because sometimes it's just x cubed. Okay, so my base is x. But sometimes it's like 8x to the 9th, right? And you want to know what that base is. Do you remember how we determine the signs in between them, the acronym for them? SOAP, same, opposite, always positive. So if this is plus or minus to start, then if it was a plus, it'll be a plus. If it was a minus, it'll be a minus. So we write the same symbol, plus or minus. God, these pens are counting. But this is the opposite. So instead of plus or minus, minus plus, minus or plus. That's what that symbol means. It just means change the sign from the one before it. But that's what the SOAP helps me remember. Same, opposite, and then always positive. Okay? So the terms are a, b, a squared, ab, b squared. And the signs in between are the same, the opposite, and always positive. Binomial times a trinomial. And if you've taken out a greatest common factor first, it cannot be factored more than that. This is an unfactorable quadratic. Okay, and this will just be linear. Okay. So you want to look out for that GCF though, because that could make a difference. And I just wanted to give you a chance to try it. Okay, but I have both stuff for you to try. I have some quadratic stuff for you to try, and I have some indifference of perfect cubes for you to try. And it's sitting on Canvas waiting for you to submit it. I guess like by tomorrow night would be fine. I put tonight, but we're way short on time from what I expected. Whoa, there's me. It's freaking me out. Like I can't even listen to myself. Like I listen to YouTube videos to make sure they work nice. And I hear myself talking. I'm like, is that really what I sound like? So I called it, is this it? No, is this it? Yeah, I called it classwork for today. Okay, and it's just sitting right here. Click here for today's work. It'll take you to that assignment on here so you can open up, but the submission can go right on there. But I wanted to do both. I wanted to give you a chance to try both kind of the quadratic side of things with these irrational roots. And maybe you try vertex form only. But I also wanted to give you a handful of the some indifference of perfect cubes so you can get a handle on that. Okay? And I'm going to give you the rest of the time to give it a shot. Okay? I'm going to start putting some work up so you can see it, to see how you're doing. I'll start with part one stuff. And hopefully I get to the point where I have all of the answers written down so that worst case scenario, you walk out of here with a couple pictures that have the right answers. You try them on your own. You check to see how you did. Cool? So that's my plan. Give you a chance in here to get a little bit of practice in, to make sure you feel good with 2.1 stuff, because like some indifference of perfect cubes isn't in the textbook. But I know how important it is, so I wanted to make sure I did that, okay? Solving with vertex form, I don't know that that shows up in the textbook anywhere, so I wanted to make sure that I talked about that today. But then I will see you virtually tomorrow via our Google Meet. There we go. I'm going to bring you with me over to the answers. And you can check the discriminant if you want. If you're at home, then you are just jumping onto that Canvas announcement for today, or just finding the classwork, what do I call it? Classwork 9/21. I think I just put today's date on it. But here we go. Give them a shot. I'm just going to do part one over here. Oh my gosh, I guess Time to throw this one away. Here we go. Come on, baby. Vertex. Oh, God. Not close. So the height was good. The angle was not. Did I get you? I'm sorry if I hit you. I quit teaching. That's it. If I can't throw a pen across the room, I just shouldn't do this job anymore. Oh, no. 6 for 14. Miserable. Okay. I'm over it. I'm not going to take this home with me, I promise. All right. So f of x. All right. So time for you to work, and then you can check to see how you did over here once you're done. Negative b over 2a, and then you plug that in. 9/8 minus 9/4 is negative 9/8, negative 17/8. Number one. Minus 4x plus 1. Ooh, that's nice. 1/2. That's pretty. Yeah. Truth. There, you can buy them used for cheap.
I had one like I've had it for like 20 years.
Right.
Like,
Yeah.
And it finally
gave
I
up.
was like,
yeah. Worth the investment. I would get the 84 Plus color edition. I would get Noel's. Yeah. And you can, get a different color if you want to tell them apart. They have a lot of different skins. You can buy them, or you can you can color on the back. Like I had somebody from my Algebra 2 class last year who took her calculator to drawing and painting and painted Patrick Star on her cover. And it was awesome. Yeah, it's cool. All right, 1/2, 1/4, negative 4, so negative 1.
So I'm going to try and put
negative 2. Okay. I think that's right. No, that can't be right. Negative. So positive? Maybe? Negative 4 is, yeah, negative 1/2. So negative 1 plus 2 plus 1 is 2. Yeah, there we go. Oh, man. All right, time to go. Yeah.
question.
Please.
Would that be 1/8, the negative 1/8 instead of negative 1/8?
So negative 3/4, so squared, so 9/16 times 2, so 9/8. But now I have 9/8 minus 9/4, so that's negative 9/8. Yeah. Yeah. Ooh, square root of 1/2. So square root of 1 over the square root of 2, which is 1 over the square root of 2. We have to rationalize. Square root of 2 over 2. Plus or minus the square root of 2 over 2.
I'm not gonna look.
Boom.
I'm gonna try. I'm not gonna look. Well, there's yeah. I'm not gonna look.
Yeah. Mhm. Mhm.
Something I can't figure out why.
Show me how you. What'd you do?
Wait a minute. My first thing is okay, go back to sleep. Okay. No.
You gotta wait for that to stop blinking. Yeah, now you can do it. Table.
Yeah. Okay.
Okay, and then what we wanted was -8/3, which is that one.
Yeah.
Which is okay. So -16.333333333333 forever. So the problem is, it's not just 0.33. It's 0.333333333333 forever. So it's changing that decimal with just 2 decimal threes into a fraction. But let's see what happens if we did like -16 point, as many as we can, and then math, arrow to fraction. So don't stop at just a couple. You need like put a whole bunch. And a calculator might understand that you're looking for that repeating decimal. I think the better option is to just drop it in, like not in the table, because it's a fraction, like -8/3. I can't really write that as a decimal nicely. To just say, okay, I'm going to go to just my regular screen right here and say, okay, 3 parentheses, -8/3 squared plus blah, 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 and just type it in. Like, just do the substitution manually.
Okay.
And let the calculator do the arithmetic. That might be better. Make sense?
Yeah.
Okay. Now some solutions to some cubes. But first, question. Yeah. Sure. Sure. You just have to add me on Naviance and tell me when you need it done by. So there's like think about what your application deadlines are.
I already put in my application. I did that's why I was sending you my transcript.
Okay.
So there's an option to like that.
Cool. Sounds good.
But they already sent me my login.
Ooh. For where? What is it?
NAU.
Oh, cool. Sweet. That's exciting.
Yeah.
Congratulations.
My best friend just got accepted.
Nice. What's up, Doran? So I took the square root of both sides. And so I had to take the square root of 1/2. Square root of fraction is the fraction of square roots. And the top is just 1. But the denominator is radical 2. So I've got this fraction here, and I have to rationalize the denominator. In order to rationalize the denominator, I need to multiply this fraction by the same number top and bottom so it doesn't get any bigger or any smaller. So I'm going to multiply by 1, but I'm going to do that in a way where I'm multiplying the top and bottom by the same number. I multiply by whatever that square root is on the bottom. That square root is -2, square root of 2. So if I multiply the top by square root of 2, it's just square root of 2. But the square root of 2 times itself is 2. So this is rationalizing the denominator. So I took this, which is really that, and I rationalized the denominator because we do not want to take a rational number like 1 and divide it into irrational pieces. I'd rather take an irrational number like square root of 2 and divide it into rational sections. All right, super fast. 11:15, right? Okay. I'm not going to get all the answers down. That's okay. But just so you see them. A plus B. A, you know what? I do it like this. I write the terms down and then I fill in the sign. Same, opposite, always positive. A cubed minus B cubed. 2 parentheses. A, B, A squared, AB. B squared, same, opposite, always positive. Plus. And here's the thing that I like to do. I like to rewrite it as the sum or difference of actual cubes. So x cubed plus 2 cubed, which is going to help me figure out x 2, x squared, 2x, 4. Same, opposite, always positive. X cubed minus 64 is really x cubed minus 4 cubed. And so we'll pick this up from here tomorrow. Now here's the deal for tomorrow as you pack yourselves up. What's going to happen is I still have to show cohort B solving with vertex form and the discriminant. So the first 10-ish minutes, 10-15 minutes of class is going to be stuff you've seen before, so go ahead and tune me out. But just get yourself logged on so that when I do start 2.2, I'll go over these. I'll post the solution so you feel really good about where you're at. But the first 10 minutes or so, you won't need to pay much attention because it'll be the stuff from today. Okay? Thanks, everybody.